Hello, hello, hello. I hope everyone's having a lovely morning. We're just going to take a couple of minutes to get set up before we jump right into the session. Grab a coffee, grab a glass of water, take a couple of minutes, and then we'll get started. Just going to make sure that everybody's getting admitted properly. So we'll give it one more minute to let people come in. It's still early in the morning, at least for me. I'm Scotland based, so this is nine o'clock on the dot. So we'll give people an extra minute to get settled, and then we can jump right in. Is that okay with you, Andrea?
Yes, absolutely.
Perfect. Okay.
Thank you.
See a couple more people just dropping in. Give it a little bit more. Okay. Shall we just get started?
Yes, we can start.
Okay, perfect. So thank you everyone for joining. I can see that there's a good few people that are watching, which is brilliant. Just a quick few notes before we jump right into the presentation. Your cameras and your mics will all be turned off, so you don't need to worry about that. And the chat function will be disabled, but we've got a Q&A section, and you can submit your questions at any time by clicking the Q&A section at the top of the screen. So feel free, whenever you've got a question, just to drop one into that section of the Teams page. Now, my name is Carolyn. I, funnily enough, work at Thermo Fisher. I am one of the technical sales specialists for flow cytometry reagents and antibodies. I'm based in Scotland. I'll be your host for this session, and the lovely Andrea will be the presenter. So I'll pass on to Andrea to introduce herself, and then we'll just jump right into the presentation.
Thank you, Caroline. Thank you, everybody, for joining today. My name is Andrea. I'm based in Spain, and I work as a technical application scientist in the panel design team. And today, in this second session of Let's Talk Flow, we are going to speak about how to assign fluorophores when building a flow cytometry panel. Let's get started. So in the previous session of Let's Talk Flow, we spoke about the relevance of antibody titration, which is always best practice when we are performing a flow experiment. It's always better to perform titration to ensure that our antibody is working in the proper conditions. There are other parameters that affect antibody performance, such as the clone, the cell type, and the staining protocol. But in addition to this, the fluorophore that is conjugated to the antibody is also very important for the performance. So if we go to this example, here we can see that we are trying to detect CD127 with an antibody conjugated to a rather dim fluorophore, the ultraviolet 496. Here you can see that the separation of the populations is not very good. It's very hard to detect the positive population. But if we change the conjugate to a brighter fluorophore, such as brilliant ultraviolet 737 or super bright 436, you can see here that the separation improves and we are able to detect a higher percentage of CD127 positive cells. So this is the topic we are going to cover today, how to select properly the fluorophores in our panel to achieve the best resolution of our population. So when we are assigning fluorophores, we are building a panel. There are three main considerations that come into place. The first one is to understand the capabilities and the limitations of our flow cytometer. This will be covered in depth in the upcoming Let's Talk Flow sessions, but today we are going to explain a little bit about this topic. Also, it is very important to match the density of our antigens to fluorophore brightness. This will be explained in details in the next part of the presentation. And also at the end of the presentation, we are going to speak about how to consider co-expression of our markers when assigning fluorophores. So the first thing we need to consider when we are building a flow panel is the instrument configuration. So we need to understand how many lasers our flow cytometry has, and also what is the exact excitation wavelength of each laser. For example, our cytometer can be equipped with a green laser or with a yellow-green laser. As you can see in the slide, the excitation wavelength of these two lasers is slightly different, and this is going to affect the efficiency of the excitation of some fluorophores, such as the very popular fluorophore PE. Also, we need to consider how many detectors we have in our cytometer that are available to detect fluorescence. This is going to tell us how many parameters we can analyze at a maximum in our flow panel, and also which are specifically the filters that are associated with each detector. All these parameters are going to tell us exactly which fluorophores we can use in our instrument, how many of them, and how we can combine them. So when we need to search for our instrument configuration, we can find it, for example, in this table format. Here in this example, you can see an attuned instrument equipped with 4 lasers. So here you can see on the left-hand side the excitation laser. You can see the 4 ones, and the filters that are associated with each laser. There here you can see the fluorophores that can be detected as an example on each one of the channels determined by the filters. And this is very important to consider when designing a panel. This is the first thing we have to take into account. As for example, here you can see that in the yellow-green laser, in this particular channel, we can detect PE, but this fluorophore is also excited by the blue laser. So we can also detect it in this channel of the blue laser. Therefore, we have to take this into account when we are building a panel. So if we are using PE here, it's not a good idea to place another fluorophore here because the PE signal will be detected in both places. So it's important to always have an overview of the full configuration. Alternatively, we can also go into our cytometer software, and most of the times we will have an option that is called filter configuration, where we can visualize the configuration as it's placed in the instrument with all the mirrors. Both options are fine to know which filters are equipped in our instrument, which wavelengths they are covering, and therefore the type of fluorophores that we can use in our panel. So here you can also see an example for a 4-laser attuned instrument. Then, jumping into the next point, as we mentioned before, we need to match the fluorophore brightness with the density of expression of our antigens. And how do we know which fluorophores are dim or which fluorophores are bright? So the answer is the stain index. The stain index is the value that is going to tell us which fluorophores are brightest and which fluorophores are the dimmest. Typically, you will see a chart like this one, where you can see the fluorophores organized from the brightest to the dimmest. This graph you are seeing in the slide is specific for an attuned instrument. And whenever possible, we highly recommend to use resources that are specific to your cytometer. For example, as we mentioned before, it's not the same to have a green laser or a yellow-green laser. Or for example, PE is not going to be having the same brightness if we have only a blue laser or if we have the yellow laser that is more efficient on its excitation. Also, the wavelengths of the filters will determine how well we can detect a fluorophore. So whenever possible, the resource that is specific for the instrument will be the best one. So here you can see how the stain index informs us about the brightness of the fluorophores. Here you can see a fluorophore with a very low staining index value in the attune instrument. You can see here that the negative and the positive population are not so well separated. And then when we check fluorophores with a higher stain index, you can see that the separation improves. Here you can see PE, which is very bright with a very high stain index value, and fluor 660, which in this instrument has a medium value. To elaborate this type of resources, usually the same type of cells is used, the same antibody clone is used, and the only thing that changes is the fluorophore. So by doing this, we can measure the influence of the fluorophore and measure its specific brightness. Now that we know which fluorophores are brighter and which fluorophores are dimmer, it's time to match them with the density of our antigens. So we need to think about which antigens we want to detect and classify them into 3 different categories that we are going to cover in detail in the next slides. We can classify them as high expressed antigens, medium expressed, or low expressed. The high expressed antigens are those that define the major cellular subsets, and those need to be matched with dim fluorophores. Then we have the antigens that are expressed at a medium intensity, and for those we need to use the medium fluorophores. So this is the easiest one. And then we have the fluorophores that are expressed at a very low level, or those, the markers that are expressed at a very low level, or the markers that we don't know how much they are expressed in our cell sample. For this, we need to use the bright fluorophores. So as a summary, high expressed markers always with dim fluorophores, low expressed markers always with bright fluorophores. To measure this antigen density, what we consider is the number of molecules per cell. And also it is important to take into account that this can vary due to the activation of the cells, functional differences, or different types of samples or tissues that we are using. So going into details, let's start with the high expressed markers. So as we said before, the high expressed markers are usually very well characterized and identified subsets of cells that are very broad and present at a high percentage in the cell sample. For example, this can be the case of CD3 in a PBMC sample from humans, healthy humans, for example. Of course, in a pathology, this can change. But if we have a healthy subject, we can expect in blood a high expression of CD3. In this example, you can see here that the expression is very well defined between negative and positive. And typically, this is what we use as our parent gate to start the gating strategy. So these markers that are highly expressed are the ones we have to assign to the dimmer fluorophores, or to those most affected by spillover coming from other fluorophores, as we are going to explain at the end of the presentation. As an example, here you have CD3 detected with fluor 506, which is typically a dim fluorophore in most of the popular flow cytometers. And other examples of dim fluorophores are FICSI or Alexa Fluor 700, although of course this depends on the specific instrument that we are using. Then we have the antigens that are expressed at a medium level. Typically, these are also well characterized and with well-defined expression patterns, but sometimes their expression is continuous. It's not clear negative or positive. And in this example, you can see interferon gamma. So these cells have been stimulated. These are CD4 T cells, and they produce upon stimulation interferon gamma. As you can see, here the positive and negatives are not so well separated, and the positive cells have different levels of expression intensity. So here it's a good idea to go for intermediate, medium fluorophores, and also take into account that these should have few spillover problems compared to the high expressed markers. In this example, we have a fluorophore that is also of a medium intensity of most instruments, brilliant ultraviolet 805, and other examples of medium fluorophores in the most popular cytometers are brilliant violet 605 and NovaFluor yellow 700. Then we have the markers with a low expression or an unknown expression in our sample. Typically, there are fewer fluorophore choices for these ones as they are produced by us, the manufacturers, in more limited choices for the conjugates. And typically, they are the critical target that we want to study in our panel. So the idea is to always save the brightest fluorophores for these low expressed markers or markers with an unknown expression. And also, it's good to assign this first, as we said before, there are often fewer fluorophore choices. In this example, you can see CD25 conjugated to a fluorophore that is also bright in most instruments, super bright 780. And as you can see here, even though the percentage of positive cells is very low, they can be detected. So this is what bright fluors are going to allow us to do, to detect the cells that are present in a very low percentage in our sample. Also, it is good to save the bright fluorophores for intracellular antigens, as typically they are not expressed at a very high level. Their staining tends to be dimmer, as it is more difficult for the antibody to access the antigen since it's inside the cell, and the populations might be less discrete, so it's going to be more difficult to define positives and negatives. Also, we need to consider that the expression levels can change if we take different donors, for example, if we are working with humans, or also by activation, if we are submitting ourselves to a treatment. Examples of bright fluorophores in the most popular instruments are, for example, PE, Alexa 4647, or PSI7. Then the last topic that we are going to cover today is co-expression. We always need to understand very well the biology of our system and be mindful of co-expression when assigning fluorophores. First of all, we need to minimize the spillover into the detector that is of most interest for us or that is assigned to a very low expressed antigen. Also, we need to avoid using fluorophores with high spectral overlap for markers that are expressed together in the same cell type. And as best practice, place the mutually exclusive markers that are never expressed together in fluorophores with spectral overlap and channels that are together. We are going to visualize this better with an example. So here we are interested in detecting NKT cells as CD3 positive, CD56 positive cells. Here we have used APC fluor780 for CD3 and APC for CD56. As you can see here, there's a spillover coming from APC fluor780 into the APC channel, as you can see in this area. Now, when we go to analyze our data, we see that it is not really possible to distinguish our double positive population. There is a high widening of the signal throughout the APC channel, and this is really not a very good way to identify our cells. If we change fluorophores for CD3 and we select fluor450, as we can see in this example, here we won't have any spectral overlap or spillover between the emission spectra of both fluors. They are very separated, and this allows us to detect our cell population of interest, the NKT cells. As you can see here, even though if they are present at a low percentage, it is possible to detect. This widening in the APC axis is called spreading error or spread. It is associated with photon counting errors in the instrument, and this is a very important parameter when performing some panel designs. Therefore, in the next Let's Talk Flow session, we are going to give some tips and tricks to design our panels around spreading error and always ensure that we have the maximum resolution. As a summary of today's talk, the first thing we have to do when designing a panel is to identify the main target of our interest for the biological question that we want to solve. and then determine antigen expression level to use the dim fluorophores for highly expressed antigens. Vice versa, we need to use the bright fluorophores for those antigens that are expressed at a low level, that are of the most interest for us, are not well resolved, are intracellular with poor access to antigen, or simply we don't know its expression level on our system. We also need to minimize spillover using the known expression patterns on our cells and space out the markers that are co-expressed by placing the markers that are never expressed together in channels that are adjacent or with spectral overlap. So just to finalize the presentation before we jump into the Q&A, I would like to introduce our panel design service. This is a free of charge service and no purchases associated. So you can contact us for any questions you might have about panel design. We can also support you designing any new panels, review any existing panels, or simply help you troubleshoot any questions or issues you might have experienced when building panels in the past. We are a team of experts fully dedicated to panel design that work all around the world. And also we are completely flexible. We can accommodate any antibodies that you already have in the lab into your panels. And we can also always accommodate your needs in panel design. To contact us, you can scan the QR code in the slide, or you can also use the link that is posted by Caroline kindly in the Q&A section. And with this, we finalize the presentation. So thank you so much for your attention.